Enzyme is a huge thing, okay? It's very important. Why? Because enzymes can do chemical reactions, can speed up chemical reactions by a factor of 1,000 or 10,000, 100,000 fold, all right, under very nice conditions, okay? You don't need to have high pressure, high heat, none of that, right? Enzymes work like magic, okay? Enzymes are also very specific, okay? So if you are a drug company that wants to make a particular chemical, a particular drug that has many chiralities, okay? Now, traditional or conventional chemical synthesis will be a nightmare, okay? So if you can properly utilize biotechnology or enzymes, you can actually get very high purity reaction. Okay? So enzymes is great, okay? So, you know, my conclusion for you guys, enzymes is great, all right? So today, this is a very short introduction to enzymes. Okay, so starting next week, we'll talk about enzymes more, but today we're just going to go over some of the fundamental stuff that we need to know. First of all, we should understand the function of enzymes, why it speeds up reaction and how it speeds up reaction. That will not just be the focus of today, it will be the focus throughout the next couple of weeks. Okay, so you want to think about why an enzyme speeds up reaction and how it speeds up reactions, okay? And then importance of substrate binding to enzymes. So that these things are some of the stuff that you should keep in mind as we're going over these lectures. Okay, enzymes. First of all, definition. Enzyme or enzymes are essentially biological catalysts, okay? They are different from what we just say proteins, okay? Not all proteins are enzymes, okay? Because some proteins can be used for structural support and other stuff. So not all proteins are enzymes, okay? And then the question for you guys is, are all enzymes proteins? Okay? There are going to be enzymes that are not proteins, but we usually give them a different name, like ribozyme or abzyme, whatever. We'll talk about that, okay? So generally speaking, when we say enzymes, they are going to be proteins that are capable of catalyzing some reaction, okay? Could be some useless reaction. As you will see today, there are some pretty not so important reactions, but there's still enzymes that do it. A catalyst is a compound that increases the rate of a chemical reaction. Okay, hopefully you guys remember that from high school. And the key idea is that a catalyst is never consumed during the reaction. Okay? You will modify the catalyst during the reaction, but at the end of the reaction, you regenerate your catalyst. Okay? So that's the one of the definition of catalyst. It's not consumed. Okay? There are different types of enzymes. We have enzymatic proteins. Okay, so usually when people say enzymes, this is what they're talking about. Proteins that have catalytic functions, so we then call them enzymes. So enzymatic proteins account for the vast majority of what we say enzymes. Okay, so which is why every time we say enzymes, you can sort of just say, okay, it's a protein. Okay, what else? You have ribozyme. At the very beginning of our class, we said, you know, the world before the evolution of cells, we probably had an RNA world. Yeah? Okay? That is because RNA can also catalyze reactions. Okay? So these are the catalytic RNAs. Why? Because RNAs can have many different shapes. Okay? If you can have different 3D shapes, you have the possibility of catalyzing a reaction. Okay? So keep that thought in mind, because that's something that we will discuss throughout our discussion regarding enzymes. Okay? The shape of the enzyme and the shape of the substrate. Okay? That's a very, very important link that you have to make there. Ribozyme, essentially, it's an RNA molecule that can have stem loops and hairpin loops, whatever, okay? And then you get some kind of function out of that. You can also have enzyme. Okay, enzyme is not something that we talk about a lot, but it is currently being developed as an enzyme. Okay, so you can actually develop using antibody because antibodies are also proteins, right? And these antibodies, because they're proteins, they can also adopt a specific shape, and then that can also be used to catalyze reactions. So our class, we're not going to pay too much attention to ribozyme and enzyme, but just so that you guys know these words exist, if you're interested, welcome to use Google, Wikipedia. I'm just kidding. Google is better. Wikipedia? No. Okay. Wikipedia it's a good source, but trust Google. Okay. And then find legitimate articles. Okay. Don't trust Wikipedia completely. Okay. Because anybody can go to Wikipedia and change stuff. Okay. But you can look up online, and there's a lot of information on enzyme and ribozyme. All right. For us, introductory biochemistry course, the most important question that you want to be asking is, wait a minute, how does an enzyme catalyze a chemical reaction? Okay, how does it speed up a chemical reaction? So that's the question that you should be asking. Before we go and talk about how it catalyzes and how it speeds up reaction, first thing first, we need to make sure we're on the same page, okay, as we're discussing. So first of all, we need to understand chemical reactions, okay, chemical reactions. Now, ultimately, all biological reactions are just chemical reactions, right? Hopefully you agree, right? All biological reactions are essentially chemical reactions, right? So, which is why, you know, back in high school we say your chemistry has to be good, because otherwise you suck at everything else, right? Which is kind of true, right? So if you want to know biochemistry and molecular biology, your fundamental understanding of chemistry has to be, you know, okay, right? Okay. All right. So in any chemical reaction, there is its thermodynamics and kinetics. So we usually look at thermodynamics of a reaction and the kinetics of a reaction. Now, thermodynamics, usually it's represented by this thing called delta G. We know the change in Gibbs free energy. A lot of times we'll have that little circle and the little prime next to the delta G. Okay, we'll talk about that. So essentially, the thermodynamics governs one thing. Does the reaction happen spontaneously? Okay? Does it require energy, or does it give off energy? If it gives off energy, then it's going to be a spontaneous reaction. So that we know from high school. So thermodynamics decides the direction of the reaction. Do you go from reactant to product, or you go from product to reactant? Okay? Very straightforward. So thermodynamics decides the direction of the reaction. Kinetics, as the word suggests, kinetics meaning fast and movement. Okay? So it dictates how fast the reaction will happen. Okay? And even though we say thermodynamics and kinetics, but actually they're in a way related. You increase the kinetics by changing the thermodynamics of the intermediates, of the active, essentially the transition state. We'll talk about that. But just remember, thermodynamics of a reaction, we look at reactant, product. That's it. Okay? Kinetics, we look at what happens between the reactant and the product. Okay? And the process. All right? Now, most importantly, a catalyst, okay, so this is like one of the most important, right? Catalyst does not change the thermodynamics of a reaction. Reaction does not become more favorable because you have a catalyst. Okay? Instead, reaction just finishes more quickly when you have a catalyst. Okay? So what does catalyst do? So what does enzyme do? It changes the kinetics of a reaction. It does not do anything with the thermodynamics of a reaction. You go from A to B. Okay? Having an enzyme will not tell you you go from A to B or B to A. Okay? It will not change the direction. Okay? That's an important thing that you just memorize. I don't care. Okay? You just have to know this. Okay? Yeah. So that's important, right? So like maybe so you guys are second years, okay? Make sure that by, if you guys are for those people in our department, or you don't even have to be in our department. If you're interested in joining us for graduate school, you're going to do this application, and then you have this interview, right? And then we're going to ask you nasty questions during the interview, right? And believe it or not, I'm going to ask you things related to this, okay? And then you tell me that, oh wait, this enzyme is good because it changes my thermodynamics of this reaction. I'm just going to fail you right away, okay? Let me just put it out there so that you guys understand, right? Enzymes does not, okay? Enzyme does not change the delta G of any reaction, okay? All right, am I clear? That please just remember, okay? Delta G is determined by the nature of the reaction and at most concentration if we're not talking about the standard energy. If we're talking about the real delta G, then concentration matters, okay? So enzymes does not do anything to that, okay? Enzymes just speed up the reaction. If the reaction favors from product back to the substrate, then enzyme will just speed that up too, okay? So it will not do anything to your direction, all right? So hopefully you guys remember that. Okay, reaction of chemicals or compounds can release or require energy, okay? And this is referring to the thermodynamics, okay? Now, thermodynamics demands that the, number one, energy is conserved, okay? Number two, universe favors increase in entropy. So what does that mean? Laws of thermodynamics 1 and 2. Okay, so back in physics you learned that. Okay, now we like to use Gibbs free energy to tell us whether or not a particular reaction will be spontaneous. Okay, or rather you should think of it as if this reaction will go towards a product or this reaction will go towards the reactant. So delta G essentially tells you the direction of the reaction. So you have A plus B becomes C and D. Do you want to make C and D, or do you want to make A and B? Okay, so it tells you the direction. So again, delta G can be split into its enthalpic and entropic contributions. This you should already know from elementary school. Okay. I'm just kidding. You don't learn this in elementary school. You learn this in middle school. You guys are smarter than I am. Middle school? High school? High school. Okay, whatever. Okay. So you learned this long time ago, okay? Now, because you have two terms, you can have the enthalpic and the entropic terms, okay? And according to your Gibbs free energy equation there, you want your delta G to be negative if you want this process to be spontaneous, okay? So if you want it to be always spontaneous, you want to have a negative delta H and a positive delta S. That's fine, all right? If you want this reaction to never happen, then you want to have a positive delta H and a negative delta S, okay? And then in the middle, you have the contribution of temperature, okay? Then at high temperature, your delta S term will dominate. At low temperature, the delta H term will dominate thermodynamics. Right? Pretty simple. Now, temperature and pressure can be looked at as energy, okay? Which is why a lot of chemical process, you sort of know that this reaction, okay, is not a favorable reaction, but you can still make it happen. That is because you can provide heat and pressure to the system so that the energy in the system is higher, so you're applying energy. So then you can get, you can drive a reaction towards your product, okay? If the standard change in Gibbs free energy is positive, then you just add a lot of heat and then maybe you'll go into the product, okay? So temperature and pressure can be looked at as energy, and increasing temperature and pressure increases the energy of the system so that you can input energy. Okay? However, we know that in biochemistry, anything higher than, 100 degrees Celsius is probably not going to run. Okay? It's just not going to happen. Actually, I take that back. There are enzymes that can do 100 degrees, right? But just not many. For you, for example, like us human beings, yeah, your enzymes will function at about 37 degrees, okay? If your body temperature drops to 20 degrees, you're dead. If your body temperature goes over 50 degrees, you're dead, okay? So the temperature window of your biological reactions is very narrow, okay? So changing the direction of the reaction using temperature, out of the question, okay? You just can't do it. You can't, okay? Pressure, same thing. We evolved to grow under this normal 1 atm pressure. Yeah, I don't know. If you try to grow on a 10 atm pressure, I don't know, would you be alive? Probably not, okay? Yeah, so that's not going to happen, right? So biologically, you have limitations on how to put energy in the system, okay? So usually in biochemistry, when we look at the direction of your reaction, okay, when we look at any A to B, we will look at the delta G prime naught, okay? Well, not prime, okay? Sorry, not prime. All right, so when we say it, it's delta G naught prime. Essentially, what does that mean, okay? Okay, did I mention this a while back? Maybe I did, okay? Essentially, it says that for delta G standard, delta G naught, okay, it's that substrate and product concentration all equal to 1 molar, okay? So that's that. And the temperature is going to be at 25 degrees, okay? So this is one of the definitions for standard state, okay, or the standard condition, not standard state. Standard condition, 25 degrees C, and pressure, we say 100 Pascal. I think that K is extra, but I don't know. But essentially, it's close to 1 atm, okay? I'm not sure about the K, right? Sorry, my math sucks. 1 atm, okay? 1 atm, so approximately there, right? So that's the normal condition that we're going to be looking at our process or our reaction. Now, so that's what the little circle means, okay? So all these stuff, that's what the little circle means. Now you have that little prime there. The little prime there essentially is talking about pH equal to 7, okay? Why do we care about pH equals to 7? That is because that sometimes in biological chemistry, you deal with protons, okay? Now, according to this definition, if a reaction is involved with protons, then proton concentration is 1 molar. If proton concentration is 1 molar, pH is like what? Like maybe 1, okay? So that's going to be very acidic, right? And your cell will not be pH 1, okay? That's just not, no, okay? No. Right, so your cell will not be at pH equals to 1. So we therefore define, say, okay, we're going to analyze the delta G by looking at pH 7, okay? So always, okay, when we describe a biochemical reaction, we usually will use delta G prime naught or delta G naught prime, whatever, okay, whichever that you feel like saying. But regardless, every time we look at the standard change in Gibbs free energy, that's what we're going to be looking at, okay? So delta G naught prime or delta G prime naught or whatever. So then in biochemistry, we essentially look at the nature of the reactions because, you know, we don't do heat, we don't do pressure, okay? So then we just look at the reaction. Is it favorable? Is it unfavorable? Okay, so this is all related to thermodynamics, okay? So this is nothing to do with kinetics yet. So what does delta G really tell us? You got this magical equation, delta G prime naught is going to be equal to the negative R times T times the natural log of KEQ. R is a constant, T is a constant, okay? So R and T constant. Why is T constant? Because it's 25 degrees, okay? Because it's 25 degrees. So T essentially is a constant in this definition, okay? But obviously, if T changes, then you will have a different notation, right? Instead of delta G naught, you will just have delta G, right? If the temperature changes. So at standard energy, we have RT constant and then natural log of KEQ, okay? And then KEQ is nothing more than the equilibrium mass action, okay? Or equilibrium constant. Basically, just product at product concentration divided by reactant concentration at equilibrium. Now, all chemical reaction, okay, all chemical reaction eventually goes to equilibrium. Okay, it wants to go to equilibrium because it wants to make delta G equals to 0. If delta G is positive, it goes backwards. If delta G is negative, it goes forward, right? So eventually, every chemical reaction wants to go towards equilibrium. This you guys know, okay? You know that, okay? This wonderful equation gives us the relationship between delta G and, delta G prime naught and KEQ. Okay, that's nice. So essentially, we say, okay, if KEQ is larger than 1, you have a negative delta G. If KEQ is equal to 1, so meaning 1 divided by 1, meaning this and this equal, right? They are equal, then delta G is 0, okay, meaning that it's at equilibrium. What do you have? Oh, yeah. So if KEQ is larger, is smaller than 1, then your delta G is going to favor the reactant. Okay, so larger the product, smaller the reactant, then delta G will be negative. Smaller the product, larger the reactant, then you're going to have smaller than 1, so you will have a positive delta G. Okay, so that's just how it is. Now, we're in the next semester, okay, maybe not this semester, but next semester, we're going to be looking at tons of delta G's, okay? So ask those guys that took biochemistry 2. For every reaction, I'm going to show you like, yeah, there's a delta G with this reaction, and it will tell you whether or not this reaction is a favorable reaction, okay? Now, if you look at this chart, okay, and then you see like, okay, on the left, I have KEQ, okay, you have 1, 10, 100, 1000, right? So if KEQ is 1000, that means that you have 1000 product per 1 reactant, right? So at the equilibrium. So meaning that this reaction really favors the product, okay? And then the associated delta G value, okay? So delta G, as you can see, delta G value is negative if the KEQ is larger than 1. If KEQ is smaller than 1, then delta G is positive. Okay, now, generally speaking, if you have a reaction, okay, that is, let's say, minus 20, okay, minus 20 or minus 30 kilojoule per mole, you can essentially consider this reaction to be almost irreversible. Do you guys know the word irreversible? Okay, meaning that once it's gone, okay? It's not coming back, okay? So once it's gone, okay? So why is that? Because, you know, if you look at this chart and you see, oh, whoa, minus 17 kilojoule per mole, you already have 10 to the third power. So that's 1,000 product to 1 reactant. So imagine if you have minus 30 kilojoule per mole, do the math there, you're going to have a huge KEQ, okay, probably like 10 to the 5 or something, meaning that you have to have a lot of the reactant, lots of the product to get 1 reactant. Okay, so having said that, do you see how delta G changes the direction of your reaction? Right? Delta G sort of decides the direction of your reaction. Okay? All right? Are we okay with this idea? Right? So anything, you know, smaller than let's say minus 20, minus 30, it's irreversible. Anything larger than 20, 30 is irreversible. Okay, so it goes both ways. Right? Okay, thermodynamics versus kinetics. Now, while some reactions are very favorable with very negative delta G, okay, but how come they're not happening spontaneously? Okay, for example, oxidation of glucose, meaning you take glucose, so this guy is glucose. You take glucose, you take oxygen in air, you burn it to carbon dioxide and water, the delta G is minus 2,800 kilojoule per mole. So equilibrium constant is going to be like ginormous, right? But then the question is, what? Like sugar is very stable, right? You don't see sugar just like lying on the table and catching on fire. even though this reaction is very, very favorable, but it's not happening. That is because, okay, you have a lot of potential energy stored in sugar. Oxidation of this sugar or glucose is spontaneous because it releases a lot of heat. However, you have a huge kinetic barrier, okay? The kinetic barrier is super large. So if you draw it, it's going to look like this is glucose, this is increasing energy, and CO2 is like right here. This is the delta G, okay? It's very, very minus, but like, yeah, your activation energy is like, well, can't draw it. It's like all the way up there, and then pops back down. So your activation energy is like super high. So then you have to get over that amount of energy before it comes back down. Yeah, that's not happening. Because if it happened, your body will be caught on fire, okay? Your body has a lot of organic substances that under combustion, you will release huge amount of energy, like huge. I'm not even kidding, especially fatty acids, right? So for those of you that are, bigger, fatter, okay? Your body it has a lot of energy, okay? So you don't see people just walking around burning fire, right? That is because the activation energy for burning biomass is way too high, okay? It's way too high, right? So it's not fast enough, right? So then you're sitting there and be like, wait a minute, you're saying this is not fast enough? So eventually if you sit there for like forever, you'll catch on fire. I guess, theoretically speaking, yeah, okay? But I think you'll die before that happens, okay? So don't worry about it. You will never catch on fire by yourself. So then the idea is that then how fast is fast, or, like how do you describe this idea of fast? Okay, so this is, now we're talking about the kinetics for any chemical reaction. You have the rate of the reaction is equal to the concentration of the reactant times it by some kind of a K value that's called rate constant. Rate constant behaves according to this Arrhenius equation, okay, where you have K is equal to some kind of constant times the exponential of minus EA over RT. R and T, again, is the gas constant times the temperature. And then here, this guy is what you should looking for and what you should care about. EA is the activation energy, okay? And activation energy, usually we write it as delta G double dagger, okay? I did not invent these terms, I just use it, okay? Double dagger, and you're just like, what the fuck, double dagger? This is a typical reaction coordinate diagram. You have increasing energy, reaction coordinate. For any reaction that has a negative delta G, you have the reactant energy, product energy, and the difference, this is the overall energy released during the reaction, okay? So after the reaction, you will release some energy, okay? This energy could be in heat, it could be molecular disorder, gain entropy, right? All delta G, every delta G will have a delta H and delta S, okay? So this release of energy could be emitting heat, or it could be increased in delta S, right? Now, you see that without enzyme, you have a huge activation energy without enzyme, so you have a large energy, okay? So this, we say, delta G double dagger, or we just say EA, okay? Same thing, okay? And of course, activation energy is always positive, okay? It's just always positive because you have to put energy in order for it to go, okay? And then once it goes over to, what do you call this point right there? Transition state, right? Once you get to the transition state, then it has the choice of going back or going forward. And actually, in reality, it does both, okay? Now, it's just that if it goes forward, okay, it's even harder for it to come back. So that's why the net result, you see it go forward. Now, what enzyme does, okay, essentially it drops this energy. Okay, you have a drop in energy for your transition state. Show you some common biological reactions, all right? You have different enzymes in nature. You have the non-enzymatic rate, meaning this reaction, okay, so these are enzymes, right? They catalyze reactions. The reaction they catalyze without the enzyme. Okay, so they could be a spontaneous reaction, but without the enzyme, that's the rate. With the enzyme, that's the rate. The amount enhancement you get from the enzyme. What do you see is that non-enzymatic reaction rates are really, really slow. Okay, for example, if we look at the last one, you have a staphylococcal nuclease. Do you guys know what a nuclease is? It's a DNA molecule, okay? Now, the non-enzymatic reaction rate is about 2 times 10 to the minus 13 power, meaning for every second you only get 2 times 10 to the minus 13 molecule, okay? Meaning to cut one molecule, you need to have 2 times 10 to the 13 second. I don't even know how many minutes that is, okay? Probably very long, all right? I'm just going to take my bet and say that's very long, all right? With an enzyme, you can get about 95 events happening per second. So if you look at the rate, what do you have? You have an enhancement for about 6 times 10 to the 14th, okay? So that's like huge. Obviously, you can see, okay, you have a large enhancement in rate, okay? So enzymes is essential to all biochemical reactions, okay? Because without enzymes, these processes will be just way too slow, okay? So then, you should really think about this, You enhance the rate by 10 to the 14th power. That's a lot. So really, the question is, you should think about, like, how does an enzyme do this, okay? Why can an enzyme do this? So that's the question that we need to be asking ourselves throughout this lecture. Reaction rate, regardless of enzyme or not, reaction rate depends on the following thing. It depends on numbers of collisions. What does that mean? Your molecules have to touch each other before they can react. They cannot just like magically react. They have to physically touch. You can't just like, hey, I see you, you react. No. So they have to touch each other. The number, meaning the more frequent they touch each other, even though that sounds kind of nasty, but the more frequent they touch each other, the faster they're going to react. Right? Energy, meaning they're moving like crazy, how hard they slam into each other. Okay? Some reaction maybe require molecule A hits molecule B at a very high speed in order to react. Number 3, you have the orientation of the molecule. If you want to react with a hydroxyl group on an alcohol, then the molecule better be touching the hydroxyl groups, right? If it touches anywhere else, it's not going to react. So the orientation of the molecule is super important. The next one, you have reaction pathway. That is to the transition state. Okay, so how do you get to the transition state? That matters, right? So obviously that's gonna affect the rate of the reaction. Okay, so if you have an easy way to get to the transition state, reaction go faster. If you have bad way to go to transition state, then it's going to be slower. Now, the question then is, how do enzymes increase reaction rate without changing temperature? Because if you look, number of collisions increases with increasing temperature. Energy of the molecule increases with increasing temperature. Orientation of the molecule doesn't really change with increasing temperature, but you have more chances of getting the right orientation. Okay? But, we can't control temperature, right? Because that's set. So, enzymes. This is very important, okay? Right? Enzyme 101, right? Super important. So, let's imagine, okay, you have a hypothetical reaction that you want to do. And this reaction is you take a metal stick, okay, like a metal chopstick, okay? You want to bend it, you want to break it. So the substrate or the reactant is a metal stick, right? It's a metal stick. The product is a broken metal stick, okay? So it's a broken metal stick. The transition state is you're bending, 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 and right before it breaks, that is the transition state. Make sense? Okay? So that's the transition state. Now, if we break this process into an energy diagram, then it looks like that. You have substrate, product, and then this guy is this. Okay, with enzyme, okay, let's say you have a magnet that stabilizes the metal stick. Okay, so you have a magnet. Magnet can provide energy, okay, to some extent, right? Magnet can provide energy because you can like stick stuff on metal sticks. Now, you have a magnet that binds to the substrate, okay? And then let's see what happens. What happens? If this magnet binds to the substrate, it makes your substrate super stable because now it becomes harder to bend the metal stick. What you see is that now you got, instead of just a stick, you have a magnet covered on it. Okay, so what this will do is it will lower the energy of the substrate. Okay, the substrate's energy decreases because it is stabilized by a magnet. You have ES, which stands for enzyme substrate, ES. You have an even larger activation energy. If you look at the third case, so now my magnet, I change the shape of the magnet that stabilizes the transition state. Okay, so here it stabilizes transition state. Essentially, okay, you can imagine this. You have a huge ass magnet. The magnet is pulling on this stick, wants to pull it upward, become like that. And then what the magnet will do is it will lower the activation energy of the transition state. So what you have is you have an ES complex. Now the ES complex compared to just S, it's about the same energy, if not a little bit higher, whatever, that's not important. But what is important is the transition state is right here, okay? Because it is stabilized. After you get stabilized transition state, now it becomes super easy to break the stick. Now, some people will ask me and say, how come it doesn't just stay at the transition state? Why do you still have to break it, right? But remember, transition state is not stable. So once you get to the transition state, you either go to the product or you go to the substrate. It's not stable at transition state. If you can get this, you can get enzyme, okay? All right, this is very important, okay? Very important. Enzyme, okay? Number one, it stabilizes the transition state, okay? Just like any catalyst. How does it stabilize transition state? It makes the shape, so enzyme has a shape, right? The shape of the enzyme favors the binding of the transition state. It does not favor the binding of the substrate. If an enzyme favors the binding of the substrate and you stabilize the substrate, congratulations, you suck, okay? You have a horrible, horrible enzyme. It's not even an enzyme, okay? Because if you bind at the substrate, you make the activation energy even larger. That means this enzyme is not even an enzyme. It's there to like sabotage your process. So, lesson number one, enzymes bind transition state, okay? And it stabilizes transition state. Enzymes work by stabilizing the transition state. And among that, number one, okay, is that enzyme will bind to the transition state. Enzyme does not bind to the substrate. Okay? I shouldn't say it does not bind to the substrate, but it binds the transition state better. You preferentially want to bind the transition state, not the substrate. Okay? If you bind the substrate, you're dead. Okay? Then it sucks. It sucks big times.